Thomas Kuhn's The Structure of Scientific Revolutions, Chapter 2. In this chapter, or essay as he refers to it, Kuhn writes about what he considers to be the route to normal science. In this chapter he elaborates on his distinction between normal and revolutionary science, and it makes for interesting reading. Early in the chapter, Kuhn suggests that textbooks offer scientists a medium through which they can arrive at a consensus. He also notes that the road to a research consensus is extraordinarily arduous. The textbook states the common problems facing a research community. There were two features he suggests are necessary for revolutionary science. Unprecedented findings, which were sufficient to draw people away from the other areas of study, suggesting that there was a competitive element to the process. 2. That revolutionary science would be sufficiently open-ended to enable others to develop theories from this. In other words, they would become stakeholders in the process. I applied the Darwin test on this. What I mean by this is that Darwin's theory of natural selection is so robust that for any philosophy of science to make predictions about science, they should hold true when applied to Darwin's theory of natural selection. For the points above, I hope the reader will agree that Darwin's work on the origin of species was both unprecedented, produced a very strong following, and also gave rise to an entire field of study which has been occupying scientists for the past 150 years. Kuhn then goes on to discuss revolutionary science in physical optics and with regards to electrical phenomenon. In both cases, he provides the reader with evidence that prior to the revolution there were many small areas of research founded on different assumptions or attempting to explain different phenomena. What comes after the revolution, in Kuhn's interpretation, is very interesting and I thought was very authentic. Thus he suggests that a language arises which can be readily understood by those outside of the research community, although this changes very rapidly. After a time, the community develops a specialized language. Those who ignore the revolutionary paradigm are, quote, bred out of the profession, unquote. The research community develops more specialized equipment to investigate ever more specialized questions. He also has some interesting things to say about different branches of science. Thus, for the social sciences, he suggests that the revolutionary paradigm may be occurring today, although this would have been some time ago when the book was originally written. However, such a grand statement should be qualified with more specific examples to support his argument. Another possibility is that the social sciences may operate differently to the natural sciences in terms of how research communities are organised, behaviours within the communities, and even the nature of the questions that are being posed. I would argue, therefore, that a much closer examination needs to be made in order to justify even simple statements of this type. The strength of his book lies in how he guides the reader from examples through to his conclusions, and there is no reason why this should be abandoned when discussing a very complex branch of science. When he refers to medicine, however, he makes an interesting observation that this is strongly driven by an external social need. He also suggests that in astronomy the first paradigms arose in prehistory, and no doubt he implies that navigation by the stars was a necessary skill for hunter-gatherers. He also notes that technology assists in gathering data necessary for the development of a science. For me, Kuhn's framing of the paradigm has another implication. My interpretation of Kuhn's paradigm is that it is a function of the minds of the scientists rather than a function of the underlying properties of the universe. In other words, revolutionary thinking isn't so much about a better understanding of the world, but rather one that is more successful engaging the scientific community.